Hello, this is Dr. Hisham Said. Welcome you to the new series of Listen To here, which will learn about stress-strain relation, a typical relation for materials. So starting here with introducing the concept of deformation and strains. So if you see here on the left side, I have a bar with a cross-sectional area of A, and when it is subjected to load P, and now it's under tension, so you have elongation of delta. Now the question, if I have now a thicker bar of area 2A, question is what will be the elongation of this bar what will be the force that we need to apply on this bar to have the same deformation we had before for the thinner bar. So to have the same deformation of delta. Give you a moment to think about it. Kind of use common sense. So if you think about it, this is kind of more beef, more material kind of to tension and elongate. So you will have double the force because you have now double the area to result in the same elongation. So that's kind of getting an idea that deformation is kind of dependent on how thick or thin this member you're trying to extend, or you can also kind of compress using a compression force. Now another question for you is if we now have a longer bar, and the question here with the same cross-sectional area, the question is how much elongation would result from a force P. So we're fixing here the force to be P, we're fixing the cross-sectional area, but now we're dealing with a longer member. So what do you think deformation here will be? Will it still be delta, less than delta, or more than delta? So think about it for a moment. And if you think about it, if I had the same cross-sectional with length L when I apply P, it results in L, delta, elongation. But now when I have double the length, now I have two L's. So every one, because both of them, if you draw the normal internal force diagram, the whole length here of the member is experiencing P internal force. So kind of you will have now double the elongation because you have the same force for the same cross-sectional area, but now the length is longer. So this example here shows that the deformation, how much the member elongates or contracts under a tensile or a tension or compression force. It depends on the magnitude of the force, it depends on the cross-sectional area of the member and the length of the member. So kind of I'm trying to put all these variables now, deflection, the length, the force, and the cross-sectional area. If you remember from lesson 1, what's this thing that relates to force in a cross-sectional area? It's stress, right? So force over the cross-sectional area is the stress. Now what thing relates deflection to length? Because deflection now is relative. It's relative to cross-sectional area, and it's most importantly relative to the length. So now I can relate deflection to the length of a member by strain. And now I can relate stress and strain. I can normalize the impact of the force on a member in terms of deflection. So I'm normalizing the force by dividing by the cross-sectional area, so to get the stress. And I'm normalizing the deflection by dividing it over the length to get the strain. So now when we study material, we're not really dealing with absolute force or absolute elongation. We're dealing with stress and strain. So strain is the change in the length against the original length. So the strain here, epsilon here, is a function, is the ratio basically between the delta, the elongation here, or the change in the length over the original length. And we're here only considering strain from normal stress. So there will cover later the strain from the other major stress, which is the shear stress. So we'll just focus here on strain for normal stresses. And you can see it's dimensionless value. So this is a length, a unit length, unit length. So dividing, you have a dimensionless value. So the strain is dimensionless. But we are careful here of writing or representing its sign. So if you have elongation, the delta becomes positive, so that the strain becomes positive. So you have tension, that's elongation relative to tension, internal force. The other way will represent contraction from a compressive force or compressive stresses. And now when you apply the load on a member and it elongates or compresses, now you can drive a relationship between stress and strain, which we call here the stress strain graph of a material. It is now a material property because you normalize the force by the cross-sectional area, and you normalize the deformation by the length of the member. So you're not dependent now on the geometry of the member. You're mainly representing here a material property, the stress-strain curve. So some of you have seen that curve before. If you're a mechanical engineering student in Santa Clara, then you've seen it in Mech 15, Intro to Material Science. So I will go through it here quickly. If you want more details, please check the textbook that provides also some explanation. But when you start with zero load, so you have zero stress, then you have zero elongation, no elongation here. Theoretically, we'll see that sometimes the lab data are kind of confusing, so you have to adjust for that. But you start from 0 and 0, and then the more load you apply, the more tension you apply on that specimen, the more elongation you have. But remember, we're plotting here sigma and the strain, epsilon. So the more stress you have, the more strain. This is what we see. It's a linear relationship. Until a limit when this linear relationship is not there anymore. So you start hit here the proportional limit. Once you beyond the proportional limit, you go into the elastic limit. And we'll discuss in one of the videos later the difference between elastic and plastic. And then your yield stress. This is the end of your elastic region and the beginning of the plastic behavior here. After that, there is yielding, and then after that, so yielding is basically you have a lot of strain for the same load or almost no, very little load, and then the material starts kind of rearranging the structural, the material structure inside. So that's why it kind of take on a lot of strain, and then starts to pick up some load after that until the ultimate stress, what we call the after that the necking point. So after that you will see that here, maybe it's not visible that much, but you start seeing a neck developing in the material that you're starting to tension. I have here some samples of the specimens we test in the lab. This is aluminum and this is a brass. Right, and you can see here if I put this one together, we have here visibly you can see the necking, the neck. Actually, once it develops a neck, this is an indication it can't take on any more load. So the load it takes is dropping, but in the same time it's extending, and then you have the failure. So during that plastic region, what happens is this necking indicates that there is a local failure here. There's some issues with some impurity or issues with manufacturing at this specific point, and this is where the failure will start to happen. But also it's indication that the failure will happen once you see necking, that the stresses on some angled point, so the orientation of the stresses here, shear is actually causing failure here. So we'll see when we cover transformation of stresses that while we apply here tension, so it's a tensile stress, internally the same point feels tension in this direction, but it can transform the load, and once you transform the load, there is shear stress developing at different orientation, and that shear stress is really the one causing failure here. And you can see it like the shape of the breakage here is kind of cone. So you will see that a lot in the lab, more discussion in that when you have the lab for the course. But once you see a cone, this is indication that even if the material was under tension, the failure here actually was contributed more to shear stress failure. The shear stress was more than the capacity of the material, which is interesting. Like you apply an axial load and then you have a shear failure. So this is what this stress strain curve you're presenting here. One thing I will note is that this is one possible shape of a stress strain curve. Every material will have a different shape, different limits, different yield stresses and all of that, but the shape is actually can be completely different. You can have actually the material up to the yield, so you have the elastic region, and then there's little deformation, that's it, the material breaks. So there is no much plasticity in that material. So in the next video, part of this lesson, we'll learn kind of more about plasticity, elasticity, ductility. So wait until we cover that in the next in that video. So remember sigma, tensile normal stress. The normal stress here is equal to P over A. Now this graph here is plotted as P over the initial area of the specimen that we're testing. Remember, there is necking happening, so the area here changes. So this necking causes that the area, the actual area that you actually would consider for failure is shrinking. This means the stress, the actual stress, is more than what you would have. So the true stress, the load is the same, but you're dividing over a reduced cross-section of the area because of the necking. So sigma, the true stress here, once you start developing that necking up to the point of ultimate stress, the true stress is more than what we call the engineering stress. So something to differentiate here, what we're developing in the lab in testing materials is engineering stress. It's something we're fixing the area and ignoring that change in the cross-sectional area. So that's something to account for or to consider when you look at these graphs and use the information. The next here, we're now focusing on that elastic region. So that part here, that thing that's linear. And we really interested into that because we love linear behaviors. We design based on linear behaviors. We don't like to deal with plastic behaviors because it's not something we can easily deal with in design. It's not proportional. So for this area here, one big property we'll learn about the material is that relation between stress and strain, that linear relation, which is represented by Young's modulus. So from this equation here, you start from 0, so sigma is equal to constant times the strain. That constant here is called Young's modulus. Every material will have a different Young's modulus. Young's modulus is also indication of material stiffness. So the higher E a material value, value a material will have, the higher this value, this means the steeper the line for the curve is, right? So the steeper means it can take on more load for less deformation. So that's stiffness. So higher E means more stiffness of the material. Now in the lab, how to define or figure out what's the yield, Young's modulus and the yield, or the yield stress. So the yield stress here is important because this is the limit we use in design. So there's this 0.2% offset method. So the idea here is you look for roughly where's the kind of a line that's representing the linear behavior in that region, and then you offset it by 0.2% strain, or 0.0002, 0.002 strain. Remember, it's a dimensionless value, so 0.002 what? It's just no units. But you kind of you're using AutoCAD or a graphical design. You will draw the line, try to match as much as you can the line to the data you have, and then you copy and offset the line 0.002 to the right. One thing to note that I'm not saying to offset it from 0, very carefully to say offset it from the line that's matching with the linear data you have, because this is the point here I mentioned before, that the data you have from the lab, this line here might not start at 0 strain. So adjusting, putting in the specimen in the machine and starting running the tests, you will have in the machine recording data, it will record the clams on the specimen will start adjusting, and before any load applied, you will have some adjustments to the clams. The specimen is not stressed yet, not taking any load yet, but you will have some strain, artificial strain. The material is not loaded, but just the clams are adjusting, and you will have artificial kind of confusing strain data. So the idea, ignore all that chunk of strain data and start your 0 from where roughly the stress-strain actual relation happens. So you will also have a chance in the lab session of the course to, in the data of a test, do the 0.2% offset to figure out the yield stress of the material. So the slope of the line will give you E, Young's modulus, and where it cuts the graph after 0.002 strain will tell you what's the yield stress. The last topic we cover in this video is Venant principle. So now it's a very simple principle. So when you have a specimen, and in our modeling of stresses and statics, we apply the load in the middle. Theoretically, we're modeling it as a point load. So this point load, when you apply it, it causes significant concentration of stresses at this point. So whatever we cover in the course, we are kind of skipping that region just right under the load point and going further into the depth of the length of the member, because at this point here, deformation and stresses start to become more uniform in some way. So there's a lot of stress concentration here, and that once you hear stress concentration is something you have to, it doesn't, our design or calculations do not consider stress concentration. You have to adjust your calculations, or you have to make clear indication that I'm analyzing a cross-section of the member that's farther away from the point of load here. So the idea here, so that Venant principle, what they came up with is they started actually doing tests and trying to model here what's the behavior. So they kind of analyzed different cross sections, and the cross section that's closest to the point load here, you see the change in the stresses is so big. It's not uniform like we assume. So sigma average here, P over A. But in reality, it's so like big swing here. Under the load, of course, you will have a big concentration of stresses, and then away from that point load, you will have minimum stresses. But if you cut the member a little farther away, then you start seeing that variation not decreasing. And if you cut furthermore, now we're talking here notation. If the width of the member is b, if you're cutting away by at least b, the variation of the normal stresses across the cross section are not that different from the average stress that we calculate numerically. So the idea here is we have to make a clear assumption that we are analyzing cross sections away by the width of the member, which is measured in B. So anything between the load and this distance, our assumptions of sigma average and calculations of it do not apply. So it's just a conceptual understanding of the calculations we're doing, the limitations, because as engineers, we have to understand the limitations and assumptions we're making when we model material, when we model systems, so we can account for that in different ways, including factor of safety or other ways that we can do that, maybe increase the cross-sectional area to account for that. So knowing your assumptions and limitations of your numerical methods is very, very important. All right, so that's the end of this part. We learned about stress-strain relation and the general look of a stress-strain curve. Remember, it's only one shape we showed, and we will cover more different shapes of that in the next parts of this lesson. We also highlight the limitations and assumptions we have with sigma average in case of point loads, which is the principle of Venant. All right, so thank you for watching. I will see you in future videos. Thank you.